Hey everyone, welcome. Today we're going to tackle a topic that, let's be honest, can feel a little intimidating, logarithms. But I want you to think about them in a totally different way. Think of them as a puzzle. And like any good puzzle, once you figure out the rules, it's actually super satisfying to solve. So let's get into it and start solving this thing together. Okay, to kick things off, check out this quote. I love it because it gets right to the point. It says, "Logarithms find the cause for an effect." So, you know how an exponent might ask, what happens if we grow for this long? Well, a logarithm flips that completely. It asks, how long did we have to grow to get this big? It's all about working backwards, finding the input for the output.
Right, so before we jump into solving anything, we've got to understand the blueprint. What is a logarithm? Anyway, in this first section, we're going to lay that foundation down so we're all on the same page.
And here's the textbook definition. A logarithm is the inverse of exponentiation. Basically, it answers this question. To what power do you have to raise a certain number to get another number? It's just the flip side of an exponent. Seriously, they're two sides of the exact same coin. This right here shows that relationship perfectly. On the left, you've got the exponential form you probably remember, b to the power of y equals x. Now look at the right. The logarithmic form is the exact same information. It's just shuffled around to solve for y, the exponent. It's just a different way to write the same thing. You really want to get comfortable with this switch because it's the key to pretty much everything we're going to do. Okay, so we've got our blueprint. Now what? Well, every good builder needs a toolbox, right? For us, when we're solving these log puzzles, our tools are the three essential log laws. So let's get that toolbox stocked and ready to go. First tool out of the box is the product rule. Think of this as your power drill. It's all about combining things. The formula shows that if you're adding two logs with the same base, you can just squish them into one single log by multiplying their insides. So the log of x plus the log of y becomes one single logarithm of x times y. This is our go-to for turning addition into multiplication. Super handy.
Next up, we've got our trusty wrench, the quotient rule. And this one's kind of the opposite. If adding logs means multiplication, what do you think subtracting them means? Yep, division. So when you subtract two logs, again, same base is key, you can combine them by dividing their arguments. The log of x minus the log of y simplifies down to the log of x divided by y. Simple, right? But so powerful.
And our third and final essential tool is the power rule. This one is so useful. Basically, if you see a number hanging out in front of a log, multiplying it, you can just swoop it up and make it an exponent inside the log. So k times the log of x is the same thing as the log of x to the power of k. This is amazing for cleaning up those coefficients that are in the way.
All right, toolbox is stocked, blueprint is understood. It is time for the main event. Let's start the project and actually use these tools to solve some log equations.
And here it is, our four-step game plan. Seriously, no matter how gnarly a log equation looks, you can always come back to these 4 steps. 1. Condense. Use those tools we just talked about to get it down to one log expression. 2. Convert. Use the blueprint to rewrite it in exponential form. Get rid of the log. 3. Solve. That's just your basic algebra. And 4, and this is the big one, check your answer. Always.
Okay, let's start with a pretty straightforward one just to get our feet wet. We've got the log base 3 of the quantity x minus 4 equals 2. Simple enough. Let's follow the game plan.
All right, let's break it down. Step 1, condense. Well, there's only one log, so done. Easy. Step 2, convert. Now we rewrite it without the log. The base is 3, so that becomes the base of our exponent. We get 3 squared equals x minus 4. See how that works? Now, step 3, solve. This is the easy part. 3 squared is 9. Add 4 to both sides and boom, x equals 13.
Okay, not bad, right? That was a good warm-up. You ready for a bit of a challenge? Let's solve this one. Log base 3 of 2 plus 2 times log base 3 of x equals log base 3 of the quantity 7x minus 3. Now this one looks a little more involved. We've got logs on both sides, a coefficient, but don't panic. The game plan is exactly the same. Let's see what's really going on here.
So first things first, step 1, condense the left side. We got to get that down to a single log. What do we do first? That 2 in front of the log, we use our power rule, tool number 3, and bring it up as an exponent on the x. Great. Now we have 2 logs being added, so we use the product rule, tool number 1, to combine them into a single log of 2 times x squared. Perfect.
And here comes the cool part. We've got log base 3 of something on the left and log base 3 of something on the right. If that's true, then the somethings have to be equal, right? So we can just drop the logs. And look what was hiding in there the whole time. A quadratic equation. Who knew? So we just rearrange it a bit, solve it, and we get two potential answers, x equals 3 and x equals 1/2. But I said potential. Are they both actually valid?
And that question brings us to maybe the most important part of this whole thing, the final inspection. You know, this is the step everyone wants to skip, but it's what makes all the difference. In logarithms, it is absolutely 100% non-negotiable.
Here it is, the golden rule of logarithms. The thing inside a log, the argument, has to be positive. No exceptions. You can't take the log of a negative number, and you can't take the log of 0. It's just not defined. Think about it. Can you raise a positive number to any power and get a negative result? Nope. So sometimes when we solve these equations, we get answers that look right on paper, but they break this rule on the original problem. We call those extraneous solutions.
This is a perfect example of why we have to check. Let's pretend we solved an equation and got two answers, 5 and -2. Let's check 5 first. We plug it back in. The log of 5, yep, that's fine. The log of 5 minus 2, which is the log of 3, also fine. Green light, x equals 5 is a good solution. Now, let's try x equals -2. The very first term is the log of -2, and stop. We can't do that. It's undefined. It breaks the golden rule. We don't even have to check the rest. X equals -2 is an extraneous solution. We have to throw it out.
So, we've gone through the blueprint, we've stocked our toolbox, we've solved the puzzles, and we've done our final inspection. But why? Why does any of this matter? Let's take a look at the finished product, where these log puzzles show up in the real world.
Believe it or not, you're using this kind of thinking all the time. When you talk about a six-figure salary, you're not counting every single dollar, you're counting the number of digits. That's a power of 10. That's logarithmic. But the real magic is how logs help us handle numbers that are wildly different in scale. The energy from a tiny earthquake versus a massive one is just an unbelievably huge difference. But the Richter scale uses logs to put it all on a simple 1 to 10 scale that our brains can actually understand. It does the same thing with decibels for sound, putting a pin drop in a jet engine on the same manageable ruler.
And that's really the core of it all. Logarithms put the universe on a human scale. They take these huge exponential concepts and let us think about them in a simple, straight line. They take things that are impossibly large or incredibly small and make them comparable. It really makes you wonder, right? What other huge, complicated things could we understand better if we just found the right way to look at them?